Thank you for your patience. We had a little bit of technical difficulties, but I think we got it resolved. And for the people online, we'll make these charts available after the presentation. So if there's an issue of seeing it, you'll have a copy after the presentation. My name is Juan Traslaviña. I support the Safety and Mission Assurance Contract. And I'm really happy to be here. And thank you for taking time from your day to be here and joining us today. Didn't know you were this popular.
I didn't either. Thank you.
I'm going to take some time to share about Dr. Cleaver because his credentials are just amazing. So I'm going to read so I don't miss anything so people can acknowledge who you are.
Okay, thank you.
Dr. Cleaver is professor and graduate program director of the Department of Physics at Baylor University in Waco. He heads the Early Universe Cosmology and String Theory, UCOS, division at Baylor's Center for Astrophysics, Space Physics and Engineering Research, which is CASPER.
Yes.
Dr. Cleaver earned his PhD at Caltech. His UCOS team conducts long-term systematic computer-based studies of global phenomenology of parameter spaces of string landscape of around 10 to the 500th possible string-derived universes, and his theorized multiverse realization. So you have to explain what that is because I read that a few times.
Okay.
Okay. Dr. Cleaver's research is also moved into the experimental and engineering design direction, supporting the spacecraft propulsion systems, which is one of the reasons you're here as well.
Exactly.
So we thank you for that. Okay, he is a member of the Icarus Interstellar, founded by his PhD graduate, Richard Obasi. Icarus Interstellar has become one of the leading nonprofit organizations researching interstellar travel technology and was one of the original recipient organizations of the DARPA NASA 100-year Starship project seed money. So pretty impressive. He has written over 75 peer-reviewed physics journal articles and conference proceedings. He is co-author of an elementary particle physics textbook, referee for 8 physics journals, member of the International Advisory Board of the Journal of British Interplanetary Society, and a member of 4 IQ and 6 Science Honor Societies. Dr. Cleaver and his wife Lisa have 3 children. His interests include flying radio-controlled model airplanes, taekwondo, scuba diving, boat sailing, and snow skiing. So without further ado, help me welcome Dr. Gerald Cleaver. Thank you.
Thank you all. Thank you. Thank you all. And I thank you all for the opportunity to visit here, to drive down from Waco and give you this presentation. I want this to be an introductory presentation. I'm not going to go into a real detailed depth in all of these the concepts and programs that I'm going to introduce. If anyone wants to have more detailed discussion afterwards, that would be fine. I'm going to talk about the projects that Icarus Interstellar is doing, in particular those that are associated with NASA's 100-year Starship and the project goal. And then I'm going to talk about the 2 areas that I've been getting involved in. Involved in Icarus, and also working with some NASA colleagues such as Sonny White here. And so, let's see. I'll start with a reminder of one thing that your director, NASA head Charles Bolden said about 2 years ago. And this is from an article involving him. A couple of years ago, at the National Press Club in Washington, D.C., Charles Bolden said that one of these days we want to get to warp speed. We want to go faster than the speed of light, and we don't want to stop at Mars. So this is a mutual goal of all of us. And so we're working with NASA and looking at different areas, not just that, but also incremental steps in NASA projects to ultimately reach that goal. And first I want to introduce Icarus Interstellar. Icarus Interstellar is a nonprofit organization. It was founded in 2011 by my graduate student, now Dr. Richard Obasi, president of it, and Dr. Andreas Ziolis, who both of them are PhD graduates from Baylor University. Our organization, we're tax exempt. We became a 501c3 in 2013. And the mission statement, it's not showing up there. Oh, we have it actually over here though. The mission of Icarus Interstellar is to realize interstellar flight before the year 2010. excuse me, 2100. You did it, yeah. A little bit too quick, too early. We will accomplish this objective by researching and developing the science and the technologies that will make interstellar flight a reality, igniting the public's interest and engaging with all those prepared to invest in interstellar exploration. We're only about a 4-year-old company, but we've grown to over 50 scientists, engineers, businessmen, futurists, and students. And I'm going to tell a little bit about what we have in that and the different projects. Again, I'm going to talk about Icarus Interstellar, and II for short, and its projects, and then my related II projects. String theory realization of the Alcubierre warp drive, and then also the Matter-Antimatter projects that I've gotten involved in. The Alcubierre warp drive was my first move in the direction of Icarus Interstellar research. That's because this was the connection between string theory and space flight. Again, some of the facts about Icarus Interstellar. We have over 50 peer-reviewed publications in leading journals, such as the Journal of the British Interstellar Society, over 80 conference and symposium presentations. We've had countless media appearances, including in the New York Times, Discovery Space News, BBC News, and many more. As I said, we're an international team of over 50 volunteers, scientists, engineers, business people, journalists, and futurists. We have active student programs, including chapters now at Rutgers and Drexel universities, and I'll go over those projects too. Variety of ongoing Starship design studies. I'll outline all of those studies too. And most nonprofit space groups now have co-membership in Icarus Interstellar. Affiliates include the British Interplanetary Society, Institute for Interstellar Studies, Tau Zero Foundation, Global Starship Alliance, which its purpose is funding space ventures, Star Voyager, Earth 2 Hub, and most recently the UCSD Starship Century Funding Coordinator. We've been appointed to coordinate the funds that UCSD collects through their Starship Century program and publications, and then to disperse those funds to other nonprofits, since we are basically taking the lead among the nonprofits. And we have a very business-like structure. We're not just going into this blind, not just all theoretical scientists and all, but we have 4 different divisions. The research, I'll talk about the various research projects. We have publicity, we have directors of the social media, web development, and television divisions, business division with fundraising, TV production, and also fundraising through gaming research. And that is turning out to be a very good monetary source. I'll talk about that maybe afterwards. And then education. We have Icarus student designers, and this involves the two different university branches. We're setting up, quote, Starflight Academy, and educational packages. And I'll go over some of those in my talk too. Future activities. The overall goal of Icarus is Icarus aspires to become synonymous with the field of credible interstellar travel among nonprofit organizations. Icarus is pursuing private donations and federal funding opportunities for the creation of educational curricula relating to interstellar engineering, research funding for Icarus stipends, office labs, and travel, the design and launch of an interstellar nanosatellite mission by 2016. I'll talk about that. And that is one with NASA. It's called Project Tintin, basically because what's launched will basically be along the size of a tin can. Icarus aspires to co-develop media for television and the internet, including movies and a series where our designers will serve as consultants. And Icarus aspires to co-develop educational video games with subjects of interstellar flight to promote public awareness of our endeavors, i.e. gaming for the Starship. Does that go forward? And we also, we're planning to build an Icarus Institute for Interstellar Studies where we can focus our attention, research, resources, fundraising, and educational programs. And as I said, we aspire to initiate a Starflight Academy where undergraduates and graduate students can receive an education in the subjects of aerospace and interstellar engineering. Now I'll go over some of the projects that we're working on and mentioning how many. And you can see we're not just a small organization. We've grown to, as I said, over 50 direct affiliates and probably at least as many associates. The initial project of Project Icarus, of Icarus Interstellar, hence the name association, is Project Icarus. This involves 28 team members, and the goal of it, it's a study about the engineering feasibility for an unpersoned, I've chosen that term rather than unmanned anymore, I think it's more appropriate, unpersoned, fusion-powered interstellar probe based on the British Interplanetary Society's earlier 1973 Project Daedalus. And the name also, Icarus was the son of Daedalus in Greek literature. We also have Project Hyperion, 9 people involved in it. It's a study involving the far-looking design for a peopled interstellar vessel. Project Forward, based on the original founder of a similar project. Beamed propulsion study using particle or radiation transmitters and sail collectors. Project Persephone, 5+, there's several students involved in this. It's a study of adaptable architecture for both starships and cities. And then the division that I'm in, the Project X, Physics, Propulsion, Power, and Project, or XP4 for short. We are in this division, we're exploring deep future and energy generation concepts. There's also Project Sentinel, which is one of our more recent ones, getting involved with SETI. It's a study in collaboration with SETI in establishing spacecraft probe means and protocols for exploring target star system for signs of extraterrestrial artifacts and extant microbial or otherwise living organisms. And so, as I said, this is a long-term project. We're now starting with SETI. We have our experimental research division. There we have Project Bifrost. It's experimental research on emerging technologies for use in space, especially advancing the use of nuclear space technologies. We have Project Helios, 5 people involved in it. It is the experimental studies and small-scale proof of concept designs for propulsion, power handling, spacecraft, self-assessment and repair, and communication systems for interstellar spacecraft. A particular focus is the practical investigation of laser-initiated pulse propulsion. Our 2 college branches are most associated with Project Helios. Then, as I mentioned, Project Tintin we're doing with NASA. I hope to launch before 2015, so 1 year left for that. It's an interstellar mission and nano-satellite spacecraft design for an interstellar precursor mission to be launched soon in collaboration with NASA, Project Phoenicia of the University of Washington, and some other collaborators. And then the most recent one, Project Longshot, which is a revisitation of the 1987 project by the same name of unmanned interstellar probe missions conducted by NASA, by a NASA-sponsored summer program for summer graduate students. Our Icarus Interstellar student designers are now revisiting NASA's project, correcting mistakes, incorporating omissions, and updating the technology to the current state of the art. And this is also NASA funded. We also then, as I mentioned, we have our public outreach programs. We have the Drexel University Icarus chapter. Good number of students involved in it and a couple of faculty members. And then we also have Rutgers University, the Icarus Research Division in their mechanical and aerospace engineering. And they are building very small scale models of the Daedalus reaction chamber from the British study of prior years. That one's not coming up. Then we also have, as I said, we're starting to develop and money and the basic ideas for the Starflight Academy, which is an education in interstellar engineering. And there, again, practical engineering designs for the students to test and learn about, including particular issues of survivability of electronics, major concern. Variance Dynamical Corporation is involved in funding for that. Icarus Interstellar also sponsored the Starship Congress in 2013 up in Dallas. We were hoping to have at least 300 attend, and we were over 400, close to 500 people attending that. Well-known speakers, current ones, and also names in space research of the past. And we've had quite a few, I won't go over the list, but we've had many recent news articles mentioning Icarus Interstellar activities. Both U.S. newspapers and many around the world. Now I'm going to talk about, with that, I want to talk about the couple of projects that I've been involved in. The first one, again, this is our XP4 division. The first project I became involved in is the Alcubierre warp drive. Miguel Alcubierre, while a graduate student at CERN, came up with the idea of how to actually obtain effectively faster than light travel. But in a way that, of course, if it's realistic, it has to be consistent with general relativity. And we know that no object formed of matter can travel faster than the speed of light. But space itself has no limit. We know that in the original inflationary stage of the Big Bang, the universe itself, space expanded at exponentially faster than the speed of light for a very brief time. We know the universe itself, even now, is expanding at a speed very, very close to the speed of light. So space itself can expand. Matter inside can't. But matter can be carried by the expansion of space itself. In the rest frame with the space around an object, that object, again, can never travel faster than the speed of light. But Alcubierre began investigating the idea of, is there any way in which humans could actually create an could artificially create an inflationary stage? And then we basically ride along with that. And he came out with his initial paper in 1994, while a graduate student at CERN. There's been over a dozen papers dealing with issues for the realization of this Alcubierre effect. And it's called Alcubierre warp drive, or more correctly, the Alcubierre warp effect, because the effect is on space-time itself. And then basically you create, science fiction can be a forerunner of real science. It really is an effect like on Star Trek. It's this warping of space, and the space bubble travels faster than the speed of light. Anything in that bubble is still at rest with the space around it. And so it's a very, very nice idea. And so I worked on it from the idea of string theory itself. Could we find application in string theory for realization of the Alcubierre effect? And the answer is yes. And that's what, it was that project that Richard had already formed, Icarus Interstellar, and I saw that connection, so he and I got involved in that. And that was also, part of that happened to be an idea that he had in his doctoral thesis also. NASA liked it, and that was one of the reasons why Richard was one of, and then our other graduate student, Andreas, were appointed as assistant directors of the 100-year Starship of NASA's project under Mae Jemison. On that, it was just this Alcubierre warp drive that did it. And if you stop and think of, if we really are going to do interstellar, we need some system that can provide at least a good fraction of the speed of light speeds. And this is probably the most advanced idea. It's probably the longest future idea that we have, but it's probably that has the greatest payoff of any if it can be realized on that. And you can consider, as Sonny White set up, you consider the real challenge of interstellar flight. If you consider something like Voyager 1, how long it will take for it to make any significant progress outside of our solar system. It's a countless period of time. Basically, as he says, it would take about 75,000 years for Voyager 1 to traverse the distance to Alpha Centauri, the nearest star, which is only for a little over 4 light years away. And if we go for, say, nuclear-powered ships, you see here the British Interplanetary Society's 1970s plan to develop a nuclear system, a nuclear ship. And there's the relative size of their Project Daedalus ship compared to Apollo. We're talking huge, massive scale. If we go conventional propulsion, or even the next step up, nuclear. So we need change of mindset ideas for interstellar travel. And Miguel came up with his paper, and the title of it was The Warp Drive, Hyperfast Travel Within General Relativity, and it was published in the peer-reviewed, top-tier Classical and Quantum Gravity journal in 1994. And as I said, there's been over a dozen peer-reviewed articles on this Alcubierre warp drive effect published to date, dealing with a range of issues. I mean, of course, it's a very complicated idea. There are serious problems have been realized, and oftentimes there have been resolution to these over the series of papers that have already come out with regard to warp drive and the Alcubierre effect. And the basic idea of it is, again, and the fundamental idea of the Alcubierre warp drive is that you have a ship that can somehow alter the expansion of space or contraction, both in front of the ship and behind a ship. So we want a more reasonable sized ship. It doesn't have to be the size of Daedalus or even Apollo. It can be, we work with basically a tentative idea of 10 by 10 by 10 cubic meter ship, something like that. What we need is to cause space in front of the ship to go against what the normal and actually contract. And you want space behind the ship to be expanding, inflating, much greater than the current expansion ratio. And then you want that, basically it's like a wave. You want the wave to move in the forward direction that you want. And then the ship is riding inside this. It's like one of the classical analogies would be a wave surfer. The person is riding the wave. He's at 0 speed relative to the wave, but the wave is propelling him on the ocean or on the water. It's the same thing here. Space contracts in front of a ship and expands behind. And if you can control, basically the cosmological constant is what causes space to expand or contract. A positive cosmological constant, which we know we have, even though it's thought to be 0 now until 97, we now know the exact value of the cosmological constant. When I say cosmological constant, same thing as vacuum energy, dark energy. We know exactly what that is, and that makes up roughly 70% of the total mass energy in the universe is due to the cosmological constant, or vacuum energy. What we want to try to do for the Alcubierre effect to work is cause the cosmological constant to become negative in front. Negative cosmological constant causes space to contract. We want to make it much more positive behind, causing it to expand. And with that effect, then it just pushes inside. I investigated this from the string theory side. And at the stage in which we totally understand string and now I should refer to it more in its current name, M theory. If we get to the point of theoretically understanding string M theory, we will know how to alter the cosmological constant. We've shown in string theory that the value of the cosmological constant is a direct function of both the size and the shape of the 7 compact directions in string M theory. Some of you may have heard 7 doesn't quite sound right. That's because for about 20 years we thought that in string theory, if string theory is true, that there were 6 compact dimensions. M theory showed that there was one extra one, and now we believe if string M theory is right, there's actually 7 compact dimensions. We have our 3 large spatial directions, time, and the 7 compact directions, giving us a total of 11 space-time directions in string M theory. And so the mathematically consistent and quantum mechanically consistent shapes that these 7 compact directions can take go by the name of Calabi-Yau manifolds. These are the shapes that you see there are 2-dimensional realizations of simple 3-dimensional versions of Calabi-Yau manifolds. They're much more complicated, but there happen to be, of the 6-dimensional versions, we have a total of about 100 trillion different Calabi-Yau manifolds. When you go to 7 compact dimensions, that number jumps up from 100 trillion to somewhere between 10 to the 100 and 10 to the 1,000. So we talk about the sort of the geometrical average and refer to it as about 10 to the 500 different consistent shapes for the 7 compact dimensions. When you alter the overall shape of the compact directions, you change the cosmological constant. When you change the size of it, you also change the value of the cosmological constant. So if we ever became understanding of string theory theoretically well enough to be able to project an instant shape and size and know exactly what the cosmological constant corresponding to that was, and then could physically alter that shape locally, we actually can control the expansion or contraction of space locally. So again, this is something that will take a long time, even admitted by string theorists, to know and to be able to do. But theoretically, we know that's how the cosmological constant can be altered locally, to have control over the compact dimensions of space-time. And so we were looking at it to, if we use that middle shape at this level, if this is flat space-time and this is the shape of the 7-dimensional compact Calabi-Yaus, if we simply keep that same shape and shrink it, that will cause the cosmological constant or vacuum energy locally to increase, and therefore that will cause a greater acceleration of that space. If we expand that shape into the limit of non-compact, that reaches the limit of 0 cosmological constant, Minkowski space, which isn't what we want. In order for space to contract, it has to have a negative cosmological constant. That means that in order to have contraction in front of the ship, the shape of the compact directions itself has to change to one that will allow a negative value. So which is why I have a different shape in front. It has to be different shape and larger. But if we could do that, a Cuvier from string theory, the Cuvier warp could be realized. Again, this is purely theoretical, but it's, again, a theoretical realization of this very profound idea that would allow near speed of light and then past speed of light, even up to factors of 10, 100, whatever, if we could control that. There've also, as I mentioned, there have been several papers that have brought up some of the issues of a Cuvier warp drive. One of them was a paper that is suggesting that even if we could alter the cosmological constant to negative in front of the ship, positive behind the ship, and neutral within the bubble itself, there is a danger for the occupants of the ship itself when they go, when they reach superluminal speed. And that is there appears to be a possible problem, and this is one of the issues that some of the other papers suggested, that there is going to be, because of the cosmological difference between the front of the ship and the rear, there will be induced radiation of high frequency and deadly for all of the occupants of the ship itself. But that only occurs if it's actual at superluminal speeds. This would allow, as a first stage, travel up to the speed of light, but sort of stopping there. There have been resolutions to this issue too, but it just says that in this general idea, there actually is a difference between subwarp and hyperwarp, or speed of light, physical effects for the ship occupants. So some of the papers deal with issues like that. Another paper suggested that a ship going through the Alcubierre warp would want to not stop directly in front of a planet, because the stopping effect itself sends out radiation forward. So if a ship stops right in front of a planet, they could actually kill all the residents of the planet they want to visit. So you stop at an angle. So there's already, we're getting into the point where physical effects like these things are being considered under the idea that the Alcubierre warp drive could actually be obtained sometime in the distant future. And so, and again, some of the ideas, some of the problems that we've had are issues that Sonny has been working on. And like the resolution of this, due to the extreme variation between cosmological constant in front and back and the radiation flow through it, are some of the issues that some of Sonny's realizations and thoughts on it resolve. So NASA itself is working on issues and finding resolutions to some of the problems of it. And so I don't want to speak for Sonny, but he's making good progress in all this, and you can talk to him directly. The other idea, I spent a few years working on that with Richard, and then more recently I've been thinking about something that is more obtainable much earlier than Alcubierre, and that is the idea of matter-antimatter propulsion systems. Those have been under study for quite a long time. I got to the idea of thinking more about backup systems for this. You know, such as one idea is collecting the matter-antimatter ahead of time. Designs for it now with some of the high energy lasers that are being obtained would allow the matter-antimatter needed to propel a craft, say to Alpha Centauri. A single high energy laser system would take about 10 years. So if you had, again, 10 of these, you could produce in the near future matter-antimatter content within about a year or so and store it. The issue that I was thinking of, if you had such a system, we really need backup. In particular, what about the emergency option if the matter-antimatter leaked, especially if there was lost magnetic containment chambers or prematurely ordinary matter leaked in? I've thought about simplest method of generating matter-antimatter, or MAM for short, on board. And this actually goes back to some of the original idea of pair production of either scalar particles or spin-a-half standard fermions from the vacuum through, again, using intense electric field quantum effects. And this was proposed very early on by one of the founders of quantum mechanics, Schwinger, and around 1950. And even earlier people, some of the original in quantum mechanics, Heisenberg and his student Euler and Sauter, all the way back in the 1930s, were proposing matter-antimatter production through quantum mechanical effects of electric fields. It was Schwinger who really put it on a sound QED, quantum electrodynamics basis. And I want to give, I was very general concepts before now. I want to go into a little more in depth and talk about how how you actually work the physics of some of these things out when you want to have a project like this. So I'll talk a little bit more detailed as I finish up my talk, as I talk about the MAM propulsion systems. Schwinger and predecessors determined early on, using quantum mechanics, that for the electron-positron, and again, electrons are the lightest mass standard model particles other than the neutrinos, which we have very little control of. So if we want to make matter-antimatter, it would be electron-positron production that we would want to do. The critical value of an electric field strength to produce electron-positrons are about 10 to the 16 volts per centimeter that you need. That will give you a sufficient potential. The strongest lasers that could produce these electric fields are right now about 1 order of magnitude below is all. For example, the X-ray free electron lasers from the LINAC coherent light source at SLAC, Sanford Linear Accelerator, and the Tesla lasers at DESY will approach the critical value in the near future. I had that, and then just a week ago I was talking to a friend at UCSB who says that, again, they're approaching the critical values probably within a few months. So this is a very apt and present possibility. And in each process, when the critical strength E0 is above this minimum value, the pair production rate, PPR, of charged particles per unit time and unit cross-section can be found, worked out from quantum mechanics of the tunneling of virtual pairs of these particles from what's known as the Dirac sea, and how to compute the production rate using what's known as instanton quantum field theory to determine the quantum mechanical tunneling probabilities is something that could be looked up in QED textbooks, actually. It's not that difficult to know. The basic idea why matter-antimatter pairs appear when a certain energy is reached. It applies in quantum mechanics what's known as the famous Dirac sea concept of matter distribution, and it also rates the cosmological constant too. The concept of both positive and negative energy states. Dirac, again, one of the founders of quantum mechanics, proposed the idea that the ground state of nature, that in the ground state of nature, all negative energy modes are filled and all positive energy modes are empty. Each mode can be assigned a certain helicity, a handedness. So let's just assume that all of the particles I'm looking at are right-handed. That'd be spin plus a half. Then the positive energy modes with positive momentum are right-handed, and the negative momentum modes are left-handed. The opposite is true for filled negative energy modes, vice versa. Again, for a combination of the electric, and I'll look at the variation, and also magnetic fields, E and B, producing sufficient potential energy density. The negative energy, I had quarks, I should put electrons in there, sorry, typo. The negative energy electrons will jump across the 2m, where m is the mass of an electron, which for 2 electrons it's about 1 MeV. This 2 mass, or 1 MeV gap between the negative energy particles forming the vacuum and the positive energy, the real ones. You don't have to have the total energy in a single spot, but you have to have it spread out tight enough in the energy density that that energy can be found within 1 Compton wavelength of a single electron. And the physical realization of this, when you have an energy density strong enough, created by an electric field and or electric and magnetic, is particle pair production. A right-handed particle in a filled energy state, and a left-handed antiparticle, a negative energy state, also seen as a hole in the negative energy vacuum by quantum mechanics, are produced. And so you can use a parallel electric and magnetic fields, and I'll deal with this, the variation, combining electric and magnetic fields to produce to become a MAM generator, which means that if a ship loses the matter-antimatter that it had in containment that had been produced on Earth for it, it could, as an emergency generator, could have strong enough electric fields and or magnetic on board to produce their own matter-antimatter. again, it's some of the ideas of Star Trek are coming true. We realized that there was sound physics underlying some of the science fiction ideas. And for these matter-antimatter propulsion systems, I can't take credit for it. The original proposer of the laser-generated matter-antimatter as a source for interstellar flight was Crow back in JBIZ again in 1983. And the idea that I'm going to get to about how the production can be enhanced when you use magnetic fields parallel to the electric field, using magnetic field enhancement of man production, was an idea that John Preskill at Caltech presented in a QCD class that he was teaching back in 1987. And the enhancement rate from another way of enhancing the production rate of electron-positron came from Gerald Dunn at University of Connecticut. He has a group that he's working with at University of Connecticut, and also he has some French science companions. They produced several papers dealing with a way of enhancing the production rate using pulsed electric fields. That's ongoing work now that he's done in the last 3 or 4 years. The idea of using this as an onboard production system, purely electric, was again one proposed by my student Richard Obosi, and then the parallel B and E onboard enhancement was one that I presented at the 100-year Starship Conference back in 2012. The idea for, again, looking at basically what's happening if you're using E-field peer production for pair production, you can use, there has to be some variation in the field to produce the particle or antiparticles. You can either have position varying E-field or a time varying E-field. What we're interested in for the critical value is the average E-field, either over space or over time. We can characterize a system by a parameter epsilon for production of a particle of mass m and charge q by the simple equation epsilon we'll define as the mass of a particle divided by the product of its charge, the magnitude of the electric field, and if it's position varying, the length of going from 0 to 0, the limits of the length of the E field. Or if it's time varying, we just simply replace length by time. And if we're using natural units and Gaussian for electromagnetics, length and time have the same overall unit. You take speed of light, c, set equal to 1. And then all you do is replace length with time in proper units. Epsilon needs to be less than 1 if you have position varying, and if it's time varying, it needs to be less than 1. But it's also allowed if it's greater than 1, but strongly suppressed, as we'll see. Sauter used all of this way back in the 1930s. And he considered a position varying E field, which is now known as a Sauter electric field, where E is a function of hyperbolic secant squared, and the E field varies effectively over a distance L. The Sauter electric field with the time varying version has also been considered. And using quantum electrodynamics, the pair production rate of charged particles per unit time and unit cross-section has been worked out. Very detailed, very complicated. I'm not going to show how it's found. But you can have the pair production rates for the case of position varying and time varying have both been worked out. And we have those rough functions. And it was computed, again, back in the 80s, that once lasers reach the critical value, which again we're approaching within a few months, a typical laser of that strength would take about 10 years for just one laser to produce the amount of matter-antimatter in electron-positron form to transport a ship at about 1/10 the speed of light from the Earth to Alpha Centauri. So that's, yeah, so that's just one laser system. So 10 can produce the amount that you need in 1 year. Or you have those on board as emergency production systems. But what we also found, actually I'd say we, I'm talking about a friend of mine by the name of Don Page, who studied under Stephen Hawking. Well known, mostly, or best known for his work on black holes. Don Page and a colleague of his, San-Pyo Kim, worked out how the particle-antiparticle production rate can be significantly enhanced if parallel is in the same direction as the E field, you have a magnetic field. And they drive these cross sections, or production rates, in the case of the presence of a B field. And what they found was that in the end, they worked out the math to it, and in the end, NLB is the production rate per unit area per unit time when you add a B field parallel to the E field. And simply L down there is the production rate without the B field. What they found was that the relationship to the rate when there is a B field versus when there's not ends up being, in simplified form, it's a ratio of the B field strength over E field times then a hyperbolic cotangent function of B over E, also with a factor pi there. And this is in Gaussian units, where C is set to 1. In real life, if we're using normal units, the B fields are viewed as always weaker, significantly weaker than the E fields by a factor of C. But in Gaussian units, where C is set to 1, B is on par with E, and in fact you can have B stronger than E. So what we see is, in the case where we have, where we add a B field that's at least as strong as E, then the production rate of the electron-positron can be significantly enhanced. And in fact, as I was saying here, let's see, just talking about the Gaussian units and all what I said. But in the end, in the case where B is significantly less than E, we see that the ratio comes out here. We end up with just small factors. The coefficients are 1 plus 1/3 of the pi B over E plus even quickly more diminuting contributions. In the case where B is less than E, NLB is effectively NL. But in the limit where B is stronger than E, again in Gaussian units, you have total enhancement by pi B over E. So you can get a significantly enhanced particle production rate by adding this parallel B field to an E field. And that makes it even, you know, the single laser 10-year can quickly become 1 year by having a B field 10 times stronger than E in Gaussian units. So that's becoming, the production rate through here is becoming much more feasible too. And this is, again, this is research that, and engineering that we are on the brink of being able to do. Let's see. And as I said, this is one way. A group, Gerald Dunn's group at University of Connecticut have also showed that you can significantly enhance the production rate through controlled engineering of special electric field pulse shapes. So engineering, again, is the key to, or I should say, combining good engineering with the underlying physics. In all of these cases is working very good. So he showed also that by well engineering the shape of the electric field variation, time in particular, you can get a significantly enhanced MAM production rate too. And he showed how you can, theoretically, you can increase the production rate as high as a factor of 10 to the 4th. And those are all, again, well-published papers. Realistically, he's shown how probably, even though theoretically by about 10 to the 4th, the simplest engineering designs can easily increase it by a factor of 10. And let's see, and that's, I'm running out of time. Let's see. just again, the person with the original idea was Devin Crow, and it was back in 1983 where he was looking at the laser strength of his day, and he correctly predicted, as we're just finding out right now, you know, within the next few months, that lasers would be approaching the critical field strength, this limit of 10 to the 16 volts per centimeter, by early into the 21st century. And at that, again, this goes into the rates that he computed back then. But once we reach this critical point, lasers, it would take about 10 years to produce the amount needed for it to take a ship at about a tenth the speed of light to Alpha Centauri. And so here, this is another area, and this is much more realistic than I would say, at least in very near term, than it could be a warp drive for producing a reasonable rate. And my research, again, was focusing on also showing how this could be done on board, in situ, for emergency propulsion systems. You can either use, I should say either or, B field enhancement and or pulse production of the E fields to significantly enhance the minimum production rate. And I'll end my research discussion there and summarize just the points that I wanted to make in my talk, and hope that I did. I wanted to point out first the growth of Icarus Interstellar. I hope that I've shown that Icarus Interstellar is making its mark in interplanetary research, including its joint efforts with NASA, SETI, and the other leading interplanetary nonprofits. We have numerous Icarus Interstellar projects that are underway, involving both solar system and interstellar applications of the ideas that we've had. And I also tried to present examples of what's happening at Icarus Interstellar with the ongoing advancements in my own research areas in the XP4 division. We talked about the Alcubierre warp effect, how it's theoretically realizable through string M theory. We're seeing now through Sonny's work simulations and models of other ways of realizing the Alcubierre warp effect through simpler ideas than string theory. We've discussed how matter-antimatter production from strong electric fields is nearing feasibility, and including enhancement of matter-antimatter production via the addition of magnetic fields parallel to the electric fields, and or the basic idea of carrier waves, that's in other words the pulsed electric fields, with oscillating frequencies that are likewise feasible to provide matter-antimatter on-demand propulsion. And I'll stop there.
Thanks very much. We're open to some questions. If anybody here or anybody online has a question, here's your time. Yes?
What would be the effect on time usage of cosmological constants?
It's local, and that's something that has been, there are papers debating that question. The overall understanding, the general belief is that it doesn't affect it. Because in the end, you're traveling in this bubble, and it starts off in flat Minkowski space and ends up in flat Minkowski space. So theoretically, the dominant understanding is nothing. But I will emphasize dominant. That is a debated issue right now. Yes.
Okay, but what then happens to causality?
Again, and that's the same thing. What we're dealing with is a physical effect that is in occurrence right now. The universe is expanding, and if we go far enough away, there are galaxies that are traveling away from us faster than the speed of light. And so the universe is causal.
Hello?
Yes, please. Somebody online?
Yes, Chris over at Kennedy.
Thank you, Chris.
What about, I couldn't hear all the questions in the background, but did anyone mention about any kind of inertial properties, such as the human physiology inside of that subspace or space bubble, the effect of acceleration?
That
Alpha 0. Proper acceleration alpha is equal to
Yeah, within the shell it is, and that's what then, especially if it's going superluminal. That is one of the issues of the accelerating, of the initial acceleration and final deacceleration, where there are some issues that are not understood as well in terms of what's happening between the bubble and space around it. Especially in superluminal, but subluminal it's controllable. But I think it is this inertial factor that causes, in the extreme limits, this radiation that could be somewhat of a hindrance. But again, through different understandings, that may be controllable. Yes.
What are the mass and energy requirements for the in-situ MAM generator as far as feedstock and just the energy necessary to convert?
Can you repeat the question?
The question is, what is the energy issue on stock on the ship? And again, we'd have to compute how much energy is going into today's lasers and how much energy it would take. Again, the one nice thing about this is, yeah, you'd have to have the energy. You'd have to compute. You can use E equals mc squared to compute what energy that would be, how much mass you're producing. The MAM production from lasers is highly efficient because it's draining, and clearly it is energy conservation. We're not saying that there's any way of avoiding that, because it's E equals mc squared, and the energy that creates the particles comes out of the E fields. And the effect here is analogous to the decay of black holes. Black holes produce particle-antiparticle production. By virtual particles are turned into real, and one usually is pulled back into the black hole and one escapes, and this is known as Hawking radiation also. And that Hawking radiation causes the gradual decay of the black hole. And here you're having the gradual decay of the electric and/or magnetic fields too. So you can figure out how much energy it is in the limit of 100% efficiency by E equals mc squared.
Before I start losing everybody, I want to just take a moment to let you know about our upcoming forums. On March 5th, Wayne Hale is going to be our guest speaker, and he's going to talk about lessons learned in the human spaceflight. So it should be an interesting presentation. Please make plans to attend. And on April 9th, Chris Hansen and Dana Wiggle will talk about the EMU water issues that we recently experienced, and they're going to share lessons learned on that. So it should be interesting topics. Please come back, and I think we have it in the same room. We also have a gift for you as a thank you for your dedication and leadership that you provided in this special topic. And here it is.
Thank you very much. I appreciate that. It looks very nice. Thank you all. And again, thank you for the invitation. I enjoyed it.
And he'll be here if you want to come up and ask some questions. But thank you all for your time. That concludes the presentation today. Bye.